Hi. In this online lecture, we will be discussing microbial responses to climate change. And at least we'll be discussing proposed or theoretical microbial responses to climate change, because as I will discuss and as I'll show you a little bit, a lot of these changes are still very much under kind of discussion and consideration by the community. I'll show you just a couple of case studies and data points where that has clearly become the case. So I want to point out that this past Friday, which is now being coined Climate Friday, the newest fourth national climate assessment has been released. This includes impacts, risks, adaptation to climate changes in the United States. These include chapters on agriculture, the Midwest, many ways that climate change is dramatically altering and is going to alter every aspect of our way of life. If you do not believe that climate change affects you, please come talk to me, because it definitely does. And if you think that you don't need to be or struggle to be someone to take action or care about climate change, you also definitely could do that, and I'm happy to help you connect those dots. So you may have also seen something like this very grim picture, but I want to assure you that while we need to take climate change very seriously, there are many, many stories of hope as well. And I will not get into so many of those things today. They are covered in the Climate Change in Agriculture lecture, and I also have a different class in the spring where I cover some of those topics. So today what we will discuss are the basics of climate change. We'll review environmental controls on microbial communities, and we'll overview how climate change could alter microbial communities and their functions. And my discussion about climate and climate change is in complement to a TED Talk that I also posted for you to watch, which is great and kind of very briefly covers how and why our climate is changing, why that we know it's us as humans that have affected the climate system on Earth. So how does our climate work? And how is our climate changing? Major climate changes include elevated CO2 by burning of fossil fuels and the change in our Earth's carbon cycle. The current level of CO2 is 406. We're nearing 410 parts per million. Warming caused by this elevated CO2 and by other changes in our atmosphere, altered precipitation regimes, and more extreme events such as droughts, floods, or hurricanes. And we've known about these changes for a long time, or at least the theory of them. And so actually in the 1890s, the idea of radiative transfer and the idea of the greenhouse effect were first established. And so it's been a long time that we've known kind of the very basics of how our Earth functions, which is the foundation we need to understand how that function or how that Earth system might change. The 60s and 70s, we understood more about sea ice, fluid dynamics. In the 90s, we started learning more about atmospheric chemistry, aerosols, and vegetation, and then finally biogeochemical cycles and carbon cycles. And so, again, this is the history of how the fundamental understanding of our climate has developed over time. And again, some of these ideas are over 100 years old at this point. I also want to give you a brief primer on the basis of the greenhouse effect. And the basic ideas were established in the mid-1800s when scientists were studying the energy balance of the Earth. So there are two processes happening here. The first is the absorption of shortwave radiation from sunlight. So the incoming sunlight is absorbed by clouds, atmosphere, the Earth's surface. Some is reflected to space, but a lot is absorbed. And the degree to which this is absorbed can depend on the nature of the surface. So you can imagine that ice would reflect a lot more radiation than a dark forest or water. And so land use change or the types of land on Earth can really affect this absorption at the Earth's surface. The second part of this is then what happens to that absorbed radiation. It is re-reflected as long-wave radiation, and it can be radiated back to space, but it also can be absorbed by clouds, by other gases in the atmosphere that we usually refer to as greenhouse gases, or other molecules in the atmosphere as well. And the degree to which this absorption happens of heat is the degree to which the Earth is warmed. So this is the basis of our science of the greenhouse effect. This is the idea of radiative forcing. So each of these different molecules, like carbon dioxide, methane, different chlorofluorocarbons, or other gases that we have introduced artificially into the atmosphere, all can trap different amounts of this heat. That's called radiative forcing. And so the more of those gases in the atmosphere, the more heat that they're trapping, this long wave radiation. So this is the basic idea of, again, how our climate system functions and how we are changing it. And you can see in this figure that carbon dioxide is kind of the main player here. And it continues to rise and rise and rise as we burn more and more and more fossil fuels. And so you may or may not have heard in the news, there's always this discussion of, how do we know that it's just not a natural variation climate? We know that there have been ice ages. We know that there are these different things that have happened to our climate over time. How do we know that it's humans? And so this is a figure produced by this newest National Climate Assessment that came out last Friday. And you could see that, the top panel, if we look at all natural drivers, they don't necessarily correspond with that black line, which is the change in temperature. And this is worldwide. So this worldwide change in temperature over time, observed since 1880, is not matching up very well if we just look at natural drivers, solar energy, orbital shifts in Earth, volcanic activity, not necessarily. Then if we look at all human influences, you could see that they match up a whole lot better. So greenhouse gases in purple, you can see how closely the greenhouse gas levels match this black line of temperature change. Ozone, land cover, aerosols actually act to cool the Earth, so you can see that it's almost a negative relationship with the amount of aerosols. And then finally, we put those all together. We have all the drivers, so any little bits of natural drivers as well as these human drivers, and you can see that there's a very close relationship. We have a good understanding of how the temperature on Earth is changing in relation to all of these different factors. And it's because, climate scientists are interested in natural functions, right? So they're not just out to study climate change per se. They are interested in studying every aspect of our climate on Earth. And then this is a little picture of our climate history, so you can see the unprecedented nature of our climate changes and our temperature change on Earth. So there's a medieval warm period. You can see the Little Ice Age. And then you can see that, in the last several hundred years, there has not been a temperature like that. And you can also see that, as I showed in the previous figures, it's around, in 1880, 1900 that we've actually been able to measure climate or the temperature on Earth. And proxies have been used before that from ice cores or other methods. If you're interested in those methods, email me and I can give you more information. Another thing that I'd like to mention here is that although this is going back several hundred years in time, one aspect of the newest climate report is that the temperatures we're heading into haven't been experienced for many thousands of years, since long before humans have been on Earth. And so we're about to enter a relatively unprecedented time in Earth's history, where we know that Earth has experienced these temperatures. Sea levels were much higher than they are now. So we know some of the physical changes that could occur on Earth from our fossil records, but there's a lot of kind of uncharted territory we are heading into. And what are we heading into? These are predictions based on different emission scenarios. So these different lines correspond to different models based on either higher or lower levels of greenhouse gas emissions. So I've shown you that we can pinpoint pretty well exactly what will cause a shift in our Earth's temperature. And you may have heard in the news that they only base these on the most dramatic emission scenarios. That is not true. They actually do lots and lots of scenario testing. And so what you can see is on the panel on the left is the global carbon emissions. So this is a range, even guessing that we might have lower emissions, like could we decrease emissions dramatically even below 1900 levels? And what would that do to our temperature change? So you could see that the temperature, if we go with those very, very low scenarios, if we very quickly, dramatically cut greenhouse gas emissions, we may stay at a 1 to 2 degree temperature change over the globe. If we continue at business as usual, that's the red line. And this is definitely based on the course we are on, not any kind of exaggeration. We will be upward to 4 to even more than 5 degrees difference. So the call is clear of what we need to do. This is a look at global temperature change. So you can see that much of the world is getting warmer and warmer. Now we'll start zooming in on the US, and then I'll zoom in and show you what Minnesota is starting to look like. So this is Minnesota, and this is the US. You can see that the upper Midwest is changing. We're much above average, slightly above average in parts of Minnesota and parts of the upper Midwest, but we are changing. This is only for 2017, and so if you look over more years, it's clear that the upper Midwest is one of the most quickly changing parts of the U.S., but 2017 was a really rough year for some of the southern states in the Southwest. And if we look at precipitation, though, we're seeing this pattern play out in Minnesota and in some areas of the upper Midwest, Michigan, Wisconsin, New York, Colorado, that are getting, or Wyoming, excuse me, where we're getting wetter and wetter climates. And so, indeed, one of the predictions in Minnesota is that we're getting warmer and wetter, not warmer and drier necessarily. I'll show you some caveats to that. But this altered Earth's climate is playing out dramatically with precipitation regimes, with rainfall, storms, where and when rain is coming, or snow or other forms of precipitation are landing in different areas. So, for example, these are climate anomalies in 2017. So the contiguous U.S. had its third warmest year on record. Every state was warmer than average. Precipitation was above average for the year. And these are just some of the things that happened. So we know from the news, Hurricane Irma, Hurricane Maria, Hurricane Harvey, Arizona, Georgia, New Mexico, North Carolina, South Carolina had their warmest year on record. Michigan was a record wet year. A record-breaking flood event impacted the mid-Mississippi Valley in the spring. We experienced some of those floods here in Minnesota as well. 66 inches of snow dropping in Erie, Pennsylvania, the last week of December. Droughts, fire, we keep hearing about wildfire in California. So these are, real changes that are very quickly accumulating. So let's turn for a minute to Minnesota's future. We will have either warm, dry or warm, wet conditions, even within the same year or across years. So one thing that could play out is that we'll have really, really wet springs, making it hard to plant crops in time, followed by very dry summers where, so the rain is falling not when the crops need it necessarily. Less predictable summer rainfall and more extreme events, longer droughts, stronger storms, or both. These are just a couple of examples from Minnesota's history that could play out in the future. So 1988, I've heard from the climatology office that this was called the Guns N' Roses summer because you could hear Guns N' Roses blaring because every person could not stand to be anywhere but the beach this summer. It was very dry, very hot. It was a miserable summer. So we could have more years like this in the future. We also could have warm and wet or just wet conditions. So 2014 started off very wet, and 2016 was very wet throughout the whole year, but was also, very, very warm. So that is climate and climate change in Minnesota. So how now will our microbes respond to climate change? So now I'll turn to the microbes and processes that we've been focusing on for most of the semester. And I will show this in just a few slides. So first I want to come back to some basic ideas. We have discussed throughout the semester how microbes are so sensitive to environmental conditions around them. And so the theme here now is that they will either have to adapt, or it'll stretch the envelope of their adaptation, or they will die, or they will move, or they will have to learn to, in the case of fungi, grow somewhere else. Microbes can't move the way that other organisms do. And so that's why we're especially concerned as well. So I'm showing this table that I showed several lectures ago on physiological adaptation or physiological limitations on microbial communities. So temperature, water stress, pH, aeration. And we know that there are adaptation methods, so temperature tolerant, enzymes and structures, salt in the cytoplasm, polysaccharide composition. So microbes have these intricate ways of dealing with their osmotic regulation and how they make sure that they have enough water, but enough of all of the kind of concentrated things in their bodies that they need. Then we have pH, which is a little bit less of a concern now, but we also have aeration. So detoxification, dormancy, ways that microbes deal with having too much or not enough oxygen. Then we have some specific adapted organisms. So we have thermophiles and psychrophiles, osmophiles and halophiles, acidophiles, and then we have aeration, so sulfur, nitrogen users, methanogens, all these obligate aerobes and anaerobes that have become very good at growing in these specific conditions. So then turning to some of our processes, this is also a slide I showed where to remind you that climate, oxygen, and temperature are some of the major controls on decomposition processes interacting with the soil resource, plant community, and plant functional types, litter quality leading into the amount of decomposition and how decomposition and carbon turnover and nutrient turnover occur in the long term. I'll show this cartoon again as well on decomposition SOM storage. At this moment, we're a little bit less concerned with the biochemical recalcitrance, a chemical and physical protection. Where the physical protection plays a role in this story is if warming leads to altered freeze-thaw cycles or multiple freeze-thaw cycles. But we also have these other environmental constraints as well. So it's too cold, I can't swim, I don't like it here. Are there constraints that protect organic matter, that have protected organic matter, that are no longer going to be relevant, like coldness or freezing? Freeze-thaw cycles also break up aggregates or cause these other physical disruptions that might, increase or change decomposition dynamics. So given microbial adaptation to local conditions, how will climate change alter these microbial communities? So the first theoretical information that we will turn to is the physiology of microbial stress responses. So we have this environmental chemistry, we have disturbance or resource availability, so stress. This leads to, microbial community composition diversity versus activity growth and resource allocation in their physiological states. And these kind of go back and forth as microbial communities adapt, compete with each other, survive, shift life strategies, and then finally outputs to different microbial processes of interest. So these are these kind of interactions of microbial structure, functional states, physiology, and how the environment plays a role in these. We also look at, carbon specifically. Again, carbon is kind of a key intersection of how, microbial communities interact and even feedback to climate. So under unstressed conditions, microbes will be growing, producing exoenzymes, extracellular enzymes for resource allocation. There'll be some maintenance CO2, but also carbon into growth, and CO2 lost in physiological material, death, turnover, building soil organic matter. This is the natural state. Under stress conditions, the major hypothesis is that microbial carbon use efficiency will decrease. And so instead of putting that energy into extracellular enzymes, exoenzymes, and carbon, now we're investing energy in protective structures, osmolytes, which are molecules used to moderate osmotic stress, survival mechanisms instead of growth. And so that carbon, that energy isn't going into building new cells, it's going into energy to protect itself. So we see a lot more CO2 going out. The efficiency is down. We see some rewetting and thaw processes depending on the moisture regime, and less carbon being stored. And so this image demonstrates this shift in carbon use because of these physiological changes of microbes under stress. And again, as I pointed out with the osmolytes, these could be different kinds of protective molecules for different stresses. So there could be different stresses for heat, there could be different stress responses for osmoregulation if it's too wet or too dry, all of these different mechanisms, but they could have similar outcomes of reduced carbon use efficiency because of the need for more energy production. So here is now a picture and a summary of how microbial communities could respond, more specifically to different climate changes. So here are changing temperature and moisture, but also elevated CO2. And I also have nitrogen here. Often in climate change or global change studies, we pair this with nitrogen deposition, because changing fertility and this altered and anthropogenically altered nitrogen cycle also play a role in how microbes respond. So elevated CO2 could cause a short-term increase in plant productivity, which would increase below-ground carbon allocation, increase carbon availability. This then will lead to nutrient imbalances, plus or minus decomposition, possible microbial feedbacks to pathogens, plant nutrient availability, depending on if this changes the carbon use efficiency, we'll see more CO2 released to the atmosphere or not. Then if we look to the other side of this figure with changing temperature or moisture, we could have all kinds of changes. We could have these stress responses I described, so plus or minus oxygen, substrate availability, direct warming or drying of the soil. This could lead to changes in decomposition and to CO2 release to the atmosphere, as I described on the previous slide. So this is how this would play out on a landscape scale. On a longer term, we could also see shifts in plant species range. So then we have different plant nutrient and water use as well, which is also a new shift for the microbial community. And so again, will they adapt to new plant communities around them? Will they stop, being efficient and functioning? Will they function at all? These are all actually still big questions, but these are the ideas of what we expect to change. And so to put this in a bit of a summary slide, warming and temperature change, short-term increases in growth or respiration, longer-term adaptation, stress responses resulting in decreased efficiency, longer-term adaptation of microbial community structure or function, higher transpiration rates lead to decreased soil moisture, added temperature and water stress, increased winter freeze-thaw cycles add an additional stress potentially, and finally that there's really no consensus prediction about long-term consequences. So we're not sure how well these microbial communities will adapt and what those adaptations will look like. Will there be another equilibrium, relatively functioning environment, or will we see more dramatic feedbacks? Similarly, in changing precipitation regimes, obligate anaerobes or aerobes will die from saturated or dry conditions respectively. Shift to different processes, implications for nutrient cycling. Microbes will need to adjust osmotic regulation in and out of their cells. And then finally, there's no consensus prediction about how long-term consequences, as with warming. So exactly what might happen is still a big question mark. And just to show you some work related to this, this is a figure about temperature regimes. So these authors had these temperate, tropical, taiga ecosystems, and they warmed all of these communities to different degrees. And what they found was that indeed there was always an increase in respiration, but only to a certain degree. So they all, around 30 degrees, hit their maximum. And the maximums are different for those different adapted environments. And then they started to go down again. So the microbial communities kind of started to hit this stress response at some point. All of them did. And so you could see that there are some question marks here in this figure. Is that temperature maxima or optimal condition, really the same in every different place, or not? That's still a question, but this phenomena seems persistent, that we, again, see these short-term increases in respiration, but that pretty quickly goes away. Then this is a chapter from my own dissertation, and one thing that we saw here was actually not a lot of changes. So we looked it's 6 years of data, and we saw lots of responses to nitrogen addition. Those are the black bars. We saw that fungal to bacterial ratios were really changing, especially to nitrogen, but also to some other factors. But the exact response to temperature, precipitation, elevated CO2, nitrogen addition, compared to the white bars in ambient were different in different years and for different communities. And our hypothesis here is that at least for the temperature and precipitation, we were still, even though we had changed the conditions, we were still kind of in range of the adaptive ability of these communities. And so perhaps we didn't kind of push the envelope enough on them to see bigger changes, or to push what happens when these communities are very, very stressed. So to summarize the microbial responses, microbes will respond to climate change in a variety of ways, including stress and adaptation responses. Consequences for the long term are still debated. And the consequences for nutrient cycles, especially for the carbon cycle, are important also, but are also largely debated or unknown. So again, will we see, big increases in decomposition, big feedbacks to carbon, leading to, a much quicker warming of the climate from decomposition and CO2 release? Or will stress responses or adaptation kind of minimize that response? Those are kind of still the questions before us. So with that, we have review questions from Catherine Hayhoe's talk and review questions from this specific lecture. Again, I'm happy to take questions about this as well. If you have any, feel free to email me. Thanks.